Hi, my name is Chanyoung. I am a master's student of School of Computing at KAIST. In this video, I will present Knowledge Graph Embedding via Metagraph Learning, which is a co-work with my supervisor, Professor Joyce Jiyoung Whang. Knowledge graph is a graphical representation of human knowledge. In a knowledge graph, each fact is represented as a triplet, which consists of a head entity, a relation, and a tail entity. Knowledge graph embedding is a representation learning technique that projects entities and relations into a feature space. Many approaches, such as translational distance models and semantic matching models, have been studied. However, most existing models do not consider a clustering structure of a knowledge graph, even though there exist many semantically close entities in a knowledge graph. We found that the semantic closeness can be inferred by the structural similarity between entities. For example, USA and Canada can be considered to be similar in this picture because they share the same head and tail entities with the same relations. In the literature, there were some attempts to incorporate entity types into a knowledge graph embedding model, but the existing methods assume the predefined entity types or require rich extra information to infer the entity types. Using the intuition that we can group semantically similar entities by just looking at the structure of a knowledge graph, we propose a way to convert a knowledge graph into a hypergraph. Then, by hypergraph clustering, we can group similar entities. Different from the existing method, our method does not require any prior information about entity types or other external features. We construct the metagraph by merging entities in the same group. After running representations on the metagraph, we can effectively initialize the corresponding entities and relations in the original knowledge graph. Now, let me describe more details of each step. To measure the structural similarity between two entities, we first identify a set of entities that share the same head or tail entity with the same relation and connect them using a hyperedge. We propose a new affinity score between two entities by considering how many common patterns are shared by those entities and how rare the patterns are. We normalize the affinity scores with respect to individual entities to appropriately compute the pairwise similarity scores. Based on these scores, we perform hypergraph clustering, which results in a set of groups of entities. Then, by merging entities in the same group, we form superentities. Based on the interactions between these superentities, we construct the metagraph, which preserves a core structure of the given knowledge graph. When constructing the metagraph, representative between group triplets are likely to be preserved, while unrepresentative triplets are likely to be dropped. Finally, we run a knowledge graph embedding method on the metagraph. Then, we initialize the corresponding entities and relations in the original knowledge graph with the learned representations. In this process, entities in the same group are initialized with the same representations. Using our affinity measure, we retrieve the topmost similar entities to a given target entity in the null dataset. For example, given a target emotion thankfulness, all these emotion-related entities were returned. Similarly, when the query is a software, the topmost similar entities are all software. These results show that our new affinity measures allows us to detect semantically close entities. We use three benchmark datasets: Freebase, NEL, and WorldNet. When creating the metagraph, we merge entities until the size of the metagraph becomes about half of the original knowledge graph in terms of the number of triplets in the training set. We measure the performance of rank prediction in terms of min rank, min reciprocal rank, and hit at 10. A positive gain here indicates that our method outperforms the original model. On these three datasets, we see that our model always shows positive total gains. As a future work, we plan to extend our model by considering overlapping clustering and multi-level clustering. If you have any questions or suggestions, please contact us at the Big Data Intelligence Lab at KAIST. Thank you.